Hello everyone, my name is Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level Chemistry exams, and this video is going to specifically focus in on hydrogen NMR. Now just to clarify, at A-Level Chemistry with the WJEC you don't need to know the theory behind how NMR operates, so this video isn't going to touch upon that. It's simply going to look at how we analyze spectrum to try and get useful information from it. So what information can we get from a hydrogen NMR? It's only going to be an introduction, I'd have thought, in this video, looking at some nice simple molecules. I'll come back perhaps in a separate video and look at some more challenging problems, and I'll also do other videos on carbon NMR as well as looking at things like mass spec and infrared, but we're just going to focus on hydrogen NMR in this video. Remember, if you find it helpful, please remember to like, subscribe and keep checking back for more content. Okay, so when we're looking at hydrogen NMR, we're looking at the number of different hydrogen environments within a molecule. So let me just try and explain what I mean by that. If you take something like CH4, nice simple one here, CH4, hopefully you can see that all four hydrogens are in the same environment. There's no chemical difference between the four hydrogens. If you go to ethane, which is CH3, CH3, hopefully you can see that once again these three hydrogens and these three hydrogens are equivalent with each other because there's a line of symmetry in the molecule. So you've only got one hydrogen environment in ethane. If you take, however, something like butanone where you've got CH3, CH2, CH3, this CH3 group would count as one hydrogen environment. This CH2 group would count as the second one. It's different. You've got a CH3 next to the CO and then a CH2 next to the CO. And then this CH3 would count as the third hydrogen environment. So you would have three different groups of peaks within butanone. Whereas if you had something like pentanone, where you've got 5 carbons, let's say pentanthreone, you've got a CH3 at each end, and then a CH2 either side of the ketone group. And this CH3 group is equivalent with this CH3 group, so you'd see one peak corresponding to that. And then this CH2 group is equivalent to this CH2 group. So in total, you would see 2 different groups of peaks within the hydrogen NMR. So the number of peaks tells you about the number of hydrogen environments. That's perhaps the first thing we can get from it. The second thing is called the chemical shift. Now, when you have an NMR spectrum, it has the x-axis going along the bottom and it's in reverse, and the x-axis normally starts at 0 on the right hand side and goes through to about 12 on the left hand side. It's really weird why it's in reverse, but we don't need to worry about that. And you're always going to be supplied with a data sheet that will tell you about the different chemical shifts, but we can pretty well summarize the main areas in terms of chemical shifts because it tells you about where the hydrogens are within the molecule. So roughly, if the chemical shift is between maybe 0 and 4, just as a rule of thumb, this corresponds to like a standard alkyl chain. If it's around 5-ish, that's an alkene, so bonded to a double bond. If it's about 7, that's benzene, so the hydrogen's on a benzene ring. If it's between 9 and 10, we're typically looking at aldehydes, so the hydrogen is part of the aldehyde group, and then carboxylic acids would be about 12. So this is a pretty good rule of thumb. However, you can get a lot more detail than this on your data sheet, so always refer to the data sheet. And that's chemical shift. It will tell you something about where that hydrogen is within the molecule. The next thing that we can get is something called coupling. This is especially important in A2 chemistry. And coupling tells you about what the hydrogen environment is next to. So you go across by 1 carbon and see how many hydrogens it is next to. So we use something called the N+1 rule, where n is the number of next door hydrogens. So if n plus 1 equals 1, we call it a singlet. And what that means is n equals 0, so there are no neighbouring hydrogens. If n plus 1 equals 2, we call it a doublet. And that means that n equals 1, and therefore there is one next door hydrogen, so it's a CH group. So you can say it's next door to a CH group. If n plus 1 equals 3, we call it a triplet. And that means n must be 2, which means it's next to a CH2 group. If n plus 1 equals 4, we call it a quartet. And that means n must be 3, so it's next to a CH3 group. There's one other scenario that's definitely worth noting, and that's if n plus 1 equals 7. We call it a septet. And that must mean it's next door to 6 hydrogens. Now that can't be a CH6 group, but it could be 2 equivalent CH3 groups. In terms of what this looks like on the NMR, a singlet would just be 1 peak, like that. A doublet would be 2 peaks of the same height. A triplet would be 3 peaks in this 1 to 2 to 1 ratio. A quartet would be 1 to 2 to 1, so you'd see 4 peaks like this. And then a septet would be 7 peaks. So that's coupling, and it tells you about what is next door to that hydrogen environment. And then lastly, we have something called integration, which you may have heard as just being called the peak area. And it's basically the height of the peak will tell you, or the area of the peak more specifically, will tell you the number of hydrogens that are in that particular environment. So if it is a CH3 group, the peak area would be 3, for instance. However, the peak areas are all relative, so it's all relative to the other peaks in the graph. But I think this is going to be easier when we look at specific examples. The way I'm going to do it in this video is relatively straightforward. I'm going to take the molecule and try and work out what we would expect the NMR to look like. In subsequent videos, I might go back and do it the other way around. So here's the NMR spectrum. What's the molecule? But for now, we'll just take a molecule and try and predict what we would expect the NMR spectrum to look like. So the first molecule I've got here is propanone. So let's draw it out. Prop means 3. You've got a ketone group on carbon number 2, and then these are CH3 groups. So the first thing to note is the number of hydrogen environments. You've got the CH3 group here and a CH3 group here, and they are equivalent to each other, so you would only expect to see 1 peak. So if this is your scale here going from 0 to 12, you're going to see 1 peak, or 1 group of peaks. And then if you go to the adjacent carbon, which is the C double bond O, you'd see that there are no hydrogens here. So n plus 1, well, it must be 0 plus 1 equals 1, so it would just be a singlet. So we're only expecting to see a singlet. In terms of the chemical shift, you go to your data sheet, and you've got all this data here. I just took this straight off the WJC data sheet, and here you can see the CH3 next to the C double bond O, so we're looking at this one. So you'd expect it to be somewhere between 2 and 2.5. So we're going to see a peak here, which is just a singlet. So we've covered the coupling is just a singlet. The chemical shift is going to be between 2 and 2.5. So we'll just call this 2, for instance. In terms of the peak area, because it's the only peak on your hydrogen NMR, the peak area is kind of irrelevant because peak areas are all relative to one another, so we can't really comment on the peak area. But technically it would equate to 6 hydrogens, but that's it. So you literally just see 1 peak for propanone, a singlet at about 2 ppm. Whereas if we take something like butanone, things get a bit more complicated. So but means 4. Then you put your ketone group, say here. Then this must be a CH3 group. this must be a CH2 group, and this must be a CH3 group. Okay, so I'm going to label the hydrogen environments A, B, and C. And then we'll make it into a little table to work out what we'd expect to see. So A, B, and C. Firstly, let's go through the peak area, nice and easy. Peak area, or the integration, tells you how many hydrogens are in each environment. So A is 3 hydrogens, B is 2 hydrogens, and C is 3 hydrogens. Next thing we could look at is chemical shift. Where would you expect it to be on the x-axis on our graph? So A is a CH3 group next to the C double bond O. So that's the same, that's this bit here, this 2 to 2.5. So we just simply write it as 2 to 2.5. B is the CH2 next to a C double bond O, and we'd expect it to be anywhere between 2 and 3 ppm. Whereas C is just a CH3 group next to an R, so we'd expect it to be about 0.9, which equates to maybe this one here, but it's quite hard to tell exactly, but it would be very low, close to about 1. Now the more challenging thing, especially if you're at A2 now, is the coupling. Let's have a look at the coupling. Try and work out what it would be. So if we look at hydrogen environment A, you've got this CH3 group, and you go across to the next carbon here, and there's no hydrogens, so n equals 0, so n plus 0 equals 1, and therefore you'd expect this to be a singlet. So on the NMR spectrum, you'd see a singlet with a peak area of 3 hydrogens, chemical shift about 2 to 2.5. When you get to hydrogen environment B, it is next door to this CH3 group. So there are 3 neighbours. So 3 plus 1 equals 4. We call that a quartet. So you'd expect it to be a 2 hydrogen quartet. So the peak area 2 and the coupling pattern would be a quartet, and you'd expect it to have a chemical shift of somewhere between 2 and 3. And then hydrogen environment C is 3 hydrogens, but it's next door to the CH2 group. So that means n equals 2. So 2 plus 1 equals 3, which is a triplet. So this is what you would expect to see for the NMR spectrum of butanone. Next up, we'll look at propanoic acid. So prop means 3. You've got a carboxylic acid group at the end, and then you put your remaining hydrogens on. And I'm going to do it the same way as I did the previous question. So there are 3 hydrogen environments. You've got the CH3 group here, which we'll just call A, the CH2 group, which we'll call B, and then the OH group, which we'll call C. So we'll make our little table again. As I've said before, this is perhaps the easier way of doing things. Here's the molecule. Let's work out what the spectrum would look like. It's more challenging to take the spectrum and work back to the structure, but I will look at that perhaps in a later video. But it's good to get the basics first. So firstly, the peak area. So the relative area of the peaks, sometimes called the integration. Well, A is a CH3 group, so it would have a relative peak area of 3. B is a CH2 group, so that would be 2. And C is only 1 hydrogen. So what this means is the peak area of A would be 3 times as big as C, and so on. Chemical shift, next. Look it up on your data sheet. Well, A is a CH3 group next to just the R group, so it's probably going to be about 0.9. B is a CH2 group next to a C double bond O, so I'd expect that to be anywhere between 2 and 3. And C is this one down here, the carboxylic acid. which is, well, about 11, but it does depend. So let's just write down what it says on the data sheet here, because that's what you'll have with you in the exams. In terms of coupling, A is next to a CH2 group, so N equals 2, so N plus 1 equals 3, so you'd expect A to be a triplet. Now B has got a CH3 group to the left, so N equals 3, so N plus 1 equals 4, so you'd expect it to be a quartet. And C is all on its own, it's got no neighbours, so N equals 0, so N plus 1 equals 1, so we call that a singlet. But the key thing for identifying a carboxylic acid group would be its chemical shift. It'd be about 11 to 12, very high. Okay, so I hope that's helpful for propanoic acid. Let's just do one more. Propanal is an aldehyde group, so you've got 1, 2, 3 carbons. You've got your aldehyde group at the end here, and then a CH2 and then a CH3. It's a little bit more complicated, this one. We'll see why in a second. So in terms of environments, there's once again going to be 3 environments. Let's call them A, B, and C. Chemical shift to start off with. Well, for A, it's this CH3 group next to an R, so once again that would be about 0.9. For B, it's the CH2 group next to a C double bond O, so that could be anywhere between 2 and 3. C is an aldehyde group, which is this one down here, which the data sheet says is about 9.8, but it does vary. So that's the chemical shift. The peak area, so the relative area of the peaks, well, A is going to be 3 hydrogens, B is going to be 2 hydrogens, and C is going to be 1 hydrogen, same as before. And then lastly, coupling. Now A is next to a CH2 group, so that's going to be a triplet. B is a more complicated situation. If you look to the left, it's coupling to a CH3 group, so you'd expect it to be a quartet, but to the right, it's coupling to a hydrogen, just one hydrogen, so that would expect to be a doublet. So you could say it's a quartet of doublets or a doublet of quartets. At A level, you wouldn't be expected to work out the detail on that. We call it a multiplet, where it couples in more than one direction, where it can couple to the left and the right, and you just expect it to be quite a complicated arrangement of peaks because it's coupling in more than one direction. We just call it a multiplet. Whereas C, the aldehyde, is coupling to the CH2 group, so you'd expect it to be a triplet on the high resolution NMR. Anyway, thank you for taking the time to watch this video. I hope it was helpful as an introduction to hydrogen NMR. I'm sure I will do subsequent videos that go into more complicated molecules and so on and so forth, but I hope it was helpful as an introduction. Remember, if you find these videos helpful, to like, subscribe, and keep checking back for more content. Thanks everyone, see you next time.